Hello and welcome everyone to the first installment of our Smart Energy webinar series. My name is Greg Bry. I work for Solar Power Events. We're the producers of Solar Power International, or SPI as many people refer to it as. Today we have Brian Patterson, president of the eMERGE Alliance. Brian will show you how the Internet of Things is empowering smart energy microgrids in what is being called the Enernet, or a network of electric energy grids and microgrids. If you have any questions, there's a Q&A area in the Zoom webinar, likely at the bottom of your screen. Feel free to ask those. We'll answer questions at the very end, as many as we can with the time permitting. But without further ado, here's Brian.
Thanks, Greg. And for those of you who aren't totally familiar with eMERGE Alliance, we're a nonprofit that's involved in writing Vanguard standards for the use of renewable energy and hybrid AC/DC microgrids in the electric power system. So without further ado, I'll jump into today's topic. And we kind of gave you already the answer to the question of what is the next big thing. But usually when we ask that question, people will dream about the things that aren't quite ready for prime time. Like wearable tech. You see my friend up there with the wearable hat, the high-tech hat there. Or things like 3D printing. For those of you who may have been at the Consumer Electronics Show, saw some 3D printed motorcycles and cars even. Maybe some people are thinking the next big thing is space travel, commercial space travel or private space travel. And there's been some moves in that direction. Or low energy transmission through the air without wire. Or maybe just effective mobile payment so you can shop around without having to dig out your credit card and things like that. So everybody's got a little bit different idea about what the next big thing is. But we really think the next big thing is bigger than any of those. And it really starts to answer the question of things that we're begging for in a much more concrete way than some of the things that you just saw on the previous slide. Most of us are looking for better security or improved health, comfort, or entertainment. Those of you who have seen WALL-E, the movie, the Pixar movie, we don't want to quite get to that state of comfort and entertainment, but we are looking for a less complicated digital world, and more of us are looking for reliable and affordable clean electricity, and more importantly, where and when you need it. And if you've been in O'Hare Airport at 5 p.m. on Friday, you know just what I mean, trying to find an outlet to plug in your cell phone charger. In any case, most of us are starting to feel the pain of moving from one venue to another, our home, our car, office. So we'd like things to start working together to support the work that we do or the leisure activities that we engage in and some of our social needs. And some of us who really want to think outside the box a little bit into augmented reality and so on, we just want logical stuff around us to happen without us having to take an active role in initiating that. So these are real things that are really on the drawing boards, in some case being delivered. And so that we don't really have to be beggars, many of us, early adopters in particular, are fast becoming choosers in this world. And they're choosing things like they want to work or live in smart buildings. They want to live and operate in a smart community or a city. They would really like to have things talk to each other through the Internet of Things, so they don't have to have a direct involvement in making things happen. Most of us would love to have solar home so we can free up some of the burden of energy cost and relieve the environmental concerns of using other forms of energy. Distributed energy resources so that we can have a more resilient energy system. And because it's getting more and more complicated, we like to see more and more autonomous intelligent controls that can do things for us without us having to turn every dial and flip every switch, if you will. A lot of this is taking the form of building and community and utility scale microgrids. where distributed energy storage is available, and the use of new and supplemental power generation like hydrogen fuel cells. And then managing a system through transactive energy management, much like the internet is managed, not from a hierarchical standpoint, but from a transactional protocol kind of platform. We're moving very quickly toward electric vehicles, which means there's a need for electric vehicle infrastructure, car charging and so on. And also in our homes and buildings, we are looking for that enhanced augmented reality, if you will, comfort and the right kind of healthy lighting and so on and so forth through electroactive enhanced environments. All of these things, though, have a sort of a common thread that runs through them in that they involve electric energy, or for the most part, electric energy. So we're seeing all of these needs and wants and desires and next big things, if you will, as tremendous market opportunities. The market opportunities going forward really are just abounding. Is initially focused a lot on solar alone, but now solar being integrated into all forms of energy systems with the help of energy storage and smart controls and so on and so forth. The whole notion of having a network or grid of grids instead of one master grid that has single points of failure, to have it broken down into microgrids that talk to each other and form a more of a mesh network topology with all the new and cleaner energy production and storage systems. So all of these things are creating market opportunities in the energy field. Part of what's going on, though, as the explosion of the use of electricity is performing more and more of our work in a clean and productive way, is the control and sensing of things. And that, of course, is being aided by the original internet, but now instead of an internet where people create data and talk to each other and share data, we're talking about machine to machine or sensor to machine kinds of things, where data is not only created but is analyzed autonomously or independently of human intervention, and so on. And this, of course, is causing an explosion of devices. I know in my own home, as I am redoing it to make it a smart home, principally solar powered, the one reality that I've already started to face is that the original wiring in my house just is insufficient in terms of the number of outlets to deliver power to all the different devices now. That includes cameras and sensors and various types of lighting and enhanced comfort features and exercise and so on. And this explosion of things are things that all have to be powered. Now, some of them, the smallest of which, may be powered by stored energy that's embedded into the device at its origin and never needs to be recharged. Other devices, if they're small enough, will harvest their own electricity enough to activate a radio that can transmit the information from the sensor or from the switch. But the vast majority of them will have to be interfaced with the electrical system to provide power to do the computational work or sensing work and so on. So this is giving rise to a lot of new thinking about how buildings get wired, with what kind of electricity, at what kind of levels. We're kind of used to the big old clunky appliances, and now many of the things we use are very low voltage and low amperage devices. Same amount of power and sometimes even less power, but divided among more and more devices. So the networks of devices and sources and so on are just becoming very dense mesh networks, if you will, of power connectivity. But the IoT is not to be dismissed because it's where the smarts for running all this stuff come from. It's comprised of all the devices down here at what I call the IoT device layer. And there's just iconic symbols down there to indicate various kinds of things that might be connected through the IoT and be controlled, but also needing, many of them needing power, electricity in particular. There is therefore a backbone of logic and communication capability. You see the IoT gateway, which will gateway out to the more traditional Wi-Fi, Ethernet, and cellular connectivity to the cloud, where data will be stored and analyzed, and various applications and device registration and rules management will take place. But more and more the user interface, when the system is not operating autonomously or semi-autonomously, will be through devices like smart hubs that we're seeing not only in the our laptops and smartphones and smart watches, but also in the voice-activated hubs. Many of you probably, if you don't already own one, have seen the Echo or the Google Home, and Apple has a hub as well, and there are some other hubs that are proprietary to various companies who are operating in this domain. The one thing about all this is that making things smart right at this point, especially for those of us who are more power integrators and not necessarily IT people, can make us kind of feel dumb, because there's so many things going on here, so many protocols, some of which are wireless, some are wired, some have low rate of data exchange, some have high rate of data exchange in the various platforms. Some of them are open protocols, some of them are proprietary protocols. So this is one of the areas that is of particular interest to many of you who are starting to look at integrating forward from what I'll call relatively passive or dumb energy systems to smart energy systems, where a lot of this IoT equipment will have to be better understood, and particularly in terms of how information is moved from sensors and devices up to the cloud and back, or even within the local networks themselves. But this is all being sorted out fairly quickly, and we're seeing a lot of movement now of gateway interfaces between different protocols that are effective. Some of you saw at the consumer show that Zigbee announced work with the Thread group, which is doing the Internet Protocol version 6, which is the expanded address for all these billions of devices that have to be named and labeled, if you will, so they can be addressable. Where the Zigbee protocol and platform will be used to interface directly with IP through the Thread protocols as well, in what's called dot. And you'll probably hear more about that as time goes on. But it's kind of typical of what's going on to simplify things and to connect the communication side of things together in a much more simple and manageable way. Well, the good news about all this is that it all needs to be powered. Well, maybe not exactly like is pictured here. Believe it or not, that's a real utility pole. Happened to be in Osaka, Japan recently, and looked up in one of the back alleys at one of the utility poles, and this is exactly what I saw. So this is not an old picture. This is actually just a couple of months old. And there were a couple actually utility workers standing at the base of this pole, scratching their heads with a big set of blueprints rolled out, trying to figure out which wire was which. So hopefully we're not going to go, we're going to be able to put in place standards and interconnection protocols that will avoid this kind of mess. And a lot of that's going to start with smart homes or smart buildings in general, but let's look at the smart home itself, where energy now is going to be produced locally in or on the home or around the home, and used either to partially serve or to entirely service the local electricity needs from time to time in the home. And here you see in this cutaway of the house here, things like solar panels on the roof, and you see the black and red cable indicating some digital power coming in, DC power coming in to the house in addition to the normal AC feeds. You see the electric cars being charged in the garage there with some batteries in various forms, forming a storage capability in addition to what's in the car itself. And then the appliances and home entertainment and home office and all the things that are around the house being connected in a smart way throughout. The difference is now buildings will be harvesting their own power in many cases, or at least supplementing what comes from the bulk power system, with the ability to store that power, whether it's produced locally or afar. That generally these microgrids include, co-located loads, some of which are temporary, like cars, some of which are more permanent, like refrigerators and appliances, and so on, and some of them transportable, like your cell phone and maybe your laptop and so on. The interesting thing about a microgrid is it is an islandable system, meaning it can be disconnected at the point of common connection with the grid. But generally, it will want to maintain some sort of a link with the rest of the power system through what's known as SCADA, or supervisory control and data acquisition links, that allow, whether you're on grid or off grid at any particular time, for you to maintain communication with what's going on. This is very important in terms of being able to provide demand response support and other forms of support to the grid, as well as for the grid to be able to support various needs of the individual homes as well. So there's a lot going on, and what you'll see is microgrids not only in the community around the home, but actually within an individual home. And the same thing is happening within factories and office buildings, whether they're specialized like data centers or warehouses or office buildings or what have you. Again, the ability to start harvesting local energy, storing it, co-locating various loads, making a system islandable so it can either stand in support or be protected from disturbances outside. Again, maintaining communication, not necessarily full control from the outside, but definitely communication to allow for supervisory response in the bulk system, as well as to provide for analytical data of what's going on in the microgrid itself. So a lot going on within buildings, or starting to go on within buildings, I should say, as these things start to ramp up in the marketplace. And utilities are also working in the microgrid area with various types of peaking plants. I'm showing here a hydrogen fuel cell example, or a wind farm, or solar farms, various types, concentrated solar, thermal heat solar, as well as photovoltaic. And of course, power storage, typically located at key points for voltage support, ride-through, disturbance ride-through capability at substations, and so on. So there's lots of different forms and use cases of utility-scale microgrids that are appearing on the landscape, if you will. And all of these microgrids are starting to get, as I call it, interconnected, E-N-E-R, energy connected between it, as well as with the communication. Here you see I'm showing basically RF communication, maybe through a LoRa or a cellular system, or some form of long-haul communication to connect with the cloud and with other elements in the grid system. In this example, a community microgrid, maybe mostly residential, starting to share power for peak requirements and startups and things like that, to avoid putting that load on the utility all the time. Same thing with commercial and industrial campuses. Again, microgrids within individual buildings being interconnected between buildings in the form of campus microgrids or business parks and so on and so forth, all communicating both between themselves, within themselves, and to the bulk power system operated by the utilities. Here again, joining in the previously mentioned utility scale microgrids into the distribution network typically. And then putting all that together in what some people call the grid of grids or grid of microgrids, but we're more and more calling it the Enernet energy network of grids. It's truly forming a grid of grids infrastructure that is highly resilient, much like the internet. And I always ask people if they remember Y2K and the disturbances then, and the answer is nobody remembers it because there weren't any, or were very few, and the ones that did occur in the internet were isolated due to the capability of what the internet does also, which is the islanding capability to manage disturbances. In any case, the this multi-tiered smart energy infrastructure will have different platforms and different protocols within the various tiers. So utilities will, by and large, still control in their own way the transmission grids and distribution grids. But as it works its way down, system works its way down into community and campuses, a tier of, I'll call it microgrid to microgrid kind of interfaces, and then individual microgrids within the building. Some people will call nanogrids or small microgrids at the building level that break all the way down into room level or device area power for different applications within various types of buildings. I'm only showing 3 tiers here. There's probably more than that will evolve over time in the Enernet, E-N-E-R-N-E-T. And again, the key to this mesh kind of network or layered or tiered structure is the interfaces between these layers and peer-to-peer interfaces across layers. And that's the part that is developing fairly rapidly now in the software and power management world. One of the key focuses in that domain is something called transactive power management. And that is to say, instead of trying to manage everything from a hierarchical standpoint, where you have a control room where humans are monitoring, where power is going and being used, and stand ready to intervene and so on, to have it operate much more like the internet, where a movement of power throughout the grid, if you will be managed transactively or semi-autonomously through rate-based supply and demand information or demand response protocols and things like that. So it'll operate much more like the grid of people, and in fact, the grid of people model will be used in many cases as prosumers get involved and want to take a more active role in how they're using energy and how energy is making them more productive or healthier or what have you. So who's going to control this new internet as it evolves is frequently the question, and the answer is everyone. Public utilities or utilities in general. There'll be probably cloud-based service providers, as there will be in the IoT. There'll be local service providers in communities and municipal activities, as well as individual prosumers who are making and using locally produced energy as well. The way that I like to think of it, and it helps me, and I hope it would help you to understand more, the simile between the internet and the Enernet. You can pretty much take the terminology that's used in the internet and find an equivalent term in the energy network or the smart energy network that will help you out. So the term network, which we use all the time in computing, and again, there's no single size or scope, if you will, for network, and nor is there in grid. You can have nanogrids, microgrids, macrogrids, global grids, just like you can have all those different size networks. Instead of moving bits, although technically in the internet, the bits are actually most of the time electrons, sometimes photons or RF waves, but energy waves, but most of the time it's electricity. It's just that the internet is almost entirely electricity, and sort of like the internet on steroids, if you will. Instead of managing data, we're actually managing electricity in the system. The equivalent of a microprocessor, perhaps, in computing is the generator in the internet. But a generation is not just rotating generators of the traditional type, but now include photovoltaics and thermal electric and hydrogen, fuel cell, and wind, and so on and so forth, all the different types of generators, much like in the computing world, the different types of microprocessors. You can use the kind of simile of memory in the computer system is like storage in the internet. And this was really key for those of you who go back a ways with the internet, in how the internet works was mostly enabled to go digital by having memory involved. So everything, computations didn't have to be real-time and dispatchable, just like electricity with the use of storage systems will not have to be real-time and dispatchable 100% of the time. You know, peripherals in the data world are really appliances in the electrical world. Mainframe computers are like utility power plants, and personal computers are more like nanogrids and solar homes and things like that. All the way down the different size networks, local, metro, and long haul, being mirrored in building, community, and macro distribution grids, bulk transmission being roughly equivalent to long haul data networks. Even the internet access points that we talk about, whether it's a Wi-Fi access or an Ethernet access, or whatever, is very similar to the point of common connection we have between grids, whether they're public or private grids. And then just as your computer can operate in a local mode and not be connected to a network, so can an Enernet, an energy network, or energy microgrid can be operated in the islanded mode and not connected. So the simile is pretty dramatic all the way down the line. When you're looking at this market develop, and as I said, it's really exploding in many directions right now with the advent of really affordable solar and storage and the capability of IoT and so on and so forth. The things you want to keep an eye on are things like there is getting to be a much greater use of direct current within these microgrids. This allows for sort of digital electrical systems and non-synchronous ones that can be synchronized through the use of inverters and can take AC power and convert it to direct current using rectifiers. So there's a lot more power electronics being incorporated into systems. Hybrid microsystems are probably going to be the most dominant form of microgrids, where both AC and DC are used depending upon the use case and application of the microgrid, how many sources it has, and what kind of loads and so on. You'll want to keep an eye on continued increase in power electronics performance, particularly in conversion electronics. You know, how efficient inverters are getting, or rectifiers are getting, or DC to DC converters, and so on and so forth. All of these will have a play on affordability and how you eventually want to control the flow of power in the system. There is an increasing diversity of equipment choices, particularly in terms of renewable energy and all the work that's been going on over the last 10 or 15 years now, not only in solar and photovoltaics and wind, but also in fuel cells and energy scavenging and harvesting, waste energy and so on, thermal electric recovery and so on. And one of the key areas that really was the key, again, in the formation of the internet is a standardization of interfaces. These points where either peer-to-peer or peer or one layer to the next or one tier to the next has to communicate. The standardization of those interfaces and what takes place at those interfaces, both physically and from a communication standpoint, is going to become key on how fast the energy network comes together. From a communication side of things, the streamlining of communication protocols. So you have sort of this one stream of data that's able to help control the flow of power and the use of devices, power devices. And I think we're going to continue to see an increasing use of open protocols to achieve that improved interoperability. And even where proprietary systems are used, they'll typically be gatewayed or designed to be gatewayed to Internet protocol, Wi-Fi, and cellular-based systems, and so on, so that the user, from a user standpoint or from a flow of information standpoint, you don't have to have one system. It's similar to the way we have Apple operating systems or Apple computer devices with Android devices and all kinds of other platforms within the computing system. I think you're going to see the same thing within the power system as well. The things that will affect the rate of this diffusion of technology into the marketplace are continuing focus on energy, but maybe not as much or not singularly driven by environmental concerns, although they're still the main driver in many cases. This integration of smart cities to be more productive, more resilient, more effective, and more economic. So the combination of drivers will tend to accelerate the adoption of smart technologies in the energy domain, and not just rely on a single driver as it did in the early days. There's also growing pressure from what I call the new millennials, who want smart buildings and smart cars and smart devices. They grew up on a diet of smart devices and electronics, and they want to continue to see that play a role in where they live and how they live, and their own health and comfort, entertainment in these buildings and cars and so on and so forth. And I think the last thing to watch is how quickly the value of the smartness of these energy systems and the resiliency of these energy systems gets monetized in value. We still talk about billion-dollar power interruption costs and things like that, but I think you're going to see even more value come out of things like improved health or improved productivity, and all the other smart and resilient energy system can give us. So with that, that really takes us from the chip to the grid and back again with the Enernet. Maybe I've lost some of you along the way, or maybe you're perplexed by what I've said, or it's left you unclear as to what I was really trying to get at. So I'm going to open it up to questions, and Greg, maybe you can see if we have any questions.
Yep. So we're having some issues with the Q&A area. So if you just add them to the chat, we'll be able to answer those with our time permitting. But the first question here, Brian, is why is it that we're seeing more use of direct current in microgrids?
That's a good question. Primarily because of the integration of a lot of different devices, both in terms of source and in terms of load. For quite some time on the load side, we've seen greater and greater use of electronics for appliances and machines and so on and so forth. It's truly a digital world, and I think most of you know that digital electronics runs on DC power for the most part, and therefore there's this desire and tendency to see if we can use DC directly. But on the sourcing side, the number of power sources that need to get connected together is going to go from a few, maybe 100,000 power sources, mostly large power plants and large gen sets and hydro dams and things like that, to millions, if not billions, of power sources all connected into the same network. And of course, those of you who are well experienced in the AC world realize that in order to combine different power generating sources together, they need to be synchronized. And to synchronize 10,000 devices is a difficult enough chore to begin with. But if we're going to millions or billions of devices that could potentially produce energy and need to be synchronized, it's better to go to direct current because they don't need to be synchronized. There's no frequency involved there. So that's one of the primary reasons. There are some other reasons that were originally brought up about DC in that solar panels, PV, and many other sources and storage in particular are natively DC. So to avoid the conversion back and forth to AC, which has a small power penalty, you could actually pick up some efficiency. But that's only one really dimension of a much larger question about synchronization and frequency control and so on. So the tendency is to be able to use DC for as long as you can or want to in collector buses and things like that, where you're combining power sources. And then once you have everything combined, then convert it to AC and through inverters to use in a more traditional distribution system. But in some of the newer systems, they are going to DC networks and loads, and so you may see an increased use, just like we have in charging our cell phone. That 5-volt USB plug is a DC plug, not an AC plug. So we're likely to see more in that direction with USB and power over Ethernet and other protocols that will be delivering DC power directly to appliances and batteries and so on and so forth. So that's where it's coming from. I don't think that we're going to see DC take over anytime soon, although technically there's lots of good reasons to think that it's probably should move faster than it is right now. But I think that we're going to see more and more use of DC in combination with AC.
Okay. So again, if you have questions, add them in the chat there. So we have one last question here, unless someone does add one to the chat area. Just in general, Brian, from what you're seeing, how do we get there? Is it from consumer demand? Does it come from, from installers really pushing this? Like, where do we get to actually where everything's starting to be more interconnected with the internet?
Well, this sort of like if pulling back, it's a little bit easier to answer that question than it was perhaps to answer how do you build an internet, the original internet, which took about 30 years in total, although many people think it happened in about half that time because they didn't see some of the early moves. But the early moves in power change in power topology, going from solely bulk power central generation to distributed generation, is going to cause a lot of this to happen. Certainly the electric vehicle movement toward electric vehicles and electric charging systems for vehicles at much higher power levels than we use for our cell phone charging and so on, is going to put demand on the system, which is going to change the way we look at power distribution and power creation. All the new clean sourcing technologies, whether it's photovoltaics and now photovoltaics kind of migrating slowly into built-in PV, where it's embedded into other materials and other structural elements of buildings, is going to make a difference in many applications. All of these things are kind of combining together to put pressure on the marketplace to move. The kind of the grunt work that has to be done is to create these many of the standards that I mentioned along the way here. Some of them have been created just exclusively in the solar energy world, dealing with connectivity of DC solar panels and how to handle that when it's in a distributed fashion, you know, at a residence or at a commercial building, what have you. So a lot of those standards have started to be written, principally the most important ones, the safety standards, but then the integration, interface standards, connectivity, voltages, power quality standards, and so on and so forth, as well as the, as I mentioned, the companion communication standards. And in many cases, there'll be sort of two levels of, I'll call it sophistication in the articulation of power. A lot of cases, there'll be simple passive controls like droop controllers and things like that, for those of you who are familiar with it, where the system just tries to maintain a voltage or a power quality parameter sort of independently of what else is going on. And then there's the very advanced notion of how to control the system with things like weather forecasting ahead of time to know whether you should charge the battery or use the solar directly, or, you know, start storing more hydrogen or whatever in the various aspects of your power system. So it kind of ranges a full gamut. You know, just like some people still use their cell phone principally for making phone calls, and others hardly touch the cell phone for its use as a phone and use it more as a very sophisticated data creation device and control device. So there'll be different strokes, different folks, I guess, on how it all gets implemented. I think the early adopters are already in the marketplace, as I say, begging for solutions. Particularly, I hate to say it this way because I'm an old geezer, but the new millennials, the younger people who are coming out of school, many of whom went and studied computer science and all the things that computers can help us do, want to see a much more sophisticated environment that utilizes big data and the articulation of their environment with the computational capability of computers. So there's lots of drivers, some of them social, some of them technical, some of them political, environmental, and so on and so forth. And I think we're brewing the, if you will, the perfect storm for there to be very significant and disruptive changes continuing in the smart energy environment.
Great, thanks, Brian. So the last question that we have here is, what does it have to do with solar?
Okay, well, the way this all started and so on is with the Solar Energy Industry Alliance Association and the Smart Electric Power Alliance, who sponsor the trade show, the Solar Power International, decided to start showing what these power systems could do, solar microgrids and smart microgrids and so on. And last year at SPI, we powered part of the show with a solar powered microgrid. This year we plan to do the same thing. This year's show is going to be at Mandalay Bay Convention Center in Las Vegas in September. And a part of the trade show floor, the Smart Energy Hall, will be powered from a microgrid, a live microgrid at the show. And so that's the connection. The primary source that we've started with for generating local power has been and will continue to be solar as we add secondary sources to it. So that's where that's coming from. The great thing about the Solar Power International show this year is that you'll get to see a lot more elements of the smart energy landscape all on one show. The solar portion of the show is probably going to be the biggest ever, but it's going to also add, as the expanded footprint caused the show management to expand the exhibit space on the show to include energy storage with Energy Storage International and with hydrogen fuel cells, and an expanded smart energy microgrid marketplace. So you'll be able to see all in one show the various elements of this smart energy smart energy landscape, and all the ways that these different aspects of energy get utilized particularly in microgrids and macrogrids. I think it's also appropriate that we wanted to make this sort of a three-part series leading up to that show. The next webinar we have is scheduled for June 21st. We're going to talk more about that transactive energy approach. In other words, how do you control a grid that has millions, if not billions, of power sources that need to be combined and managed in various size microgrids, all the way from individual rooms, maybe somebody's tiny home, all the way up to massive power plants like the Seven Gorges Dam in China, using, I think it's 800, if I'm not mistaken, it's 800,000 volt power coming off that dam, DC power that gets converted to AC eventually. In any case, we're going to talk about transactive energy and how that works into microgrids and on both sides of the meter. And then we'll have another webinar on August 2nd where we're going to preview some of the things that are going to be demonstrated and shown at Smart Energy Week. So that'll be an interesting webinar to give people sort of a sneak peek of what's going to be at the show and how it's going to work. If there's anybody out there that's interested in actually participating in our live demonstrations at the show, we do have special exhibitor opportunities. We're not going to talk about it today, but we're in a follow-up email that you'll get as a result of signing up to this. We'll ask you if you're interested, and if you say you are, there'll be a special webinar to talk about the live smart microgrid demonstration and some of the other demonstrations that will be at the show that you might want to participate in as an exhibitor. So I won't belabor that, but stay tuned for that. Check your email when you get it, and if you're interested, you can let us know.
Thanks, Brian. So that's all we have today for you. Again, we'll send a follow-up email that'll include the presentations here of all the slides, and we're also recording the session, so we'll be able to send that out to you as well. So thank you for joining us. We hope you can register for our June 21st webinar upcoming. And if you have any questions, just send a reply on the email that we'll be sending out shortly, and we'll be more than happy to help you out. Thank you.